All right. Hey, everybody. We are going to talk about, in this video, vector function derivatives. So let's just define it. There's not going to be much surprising about how we define it. So let's start with a vector function. Let's say I have the function. I'm going to make this a little bigger. So let's say I have a function r of t, and I'll give it component names: x of t, y of t, z of t. All right, those are the component functions. So we will define our derivative dr dt, very similar to the definition of derivatives that you've seen before. The limit as h goes to 0 of r of t plus h minus r of t divided by h, right? So it looks very familiar. We're just looking at a vector function now. So let's think about what this means geometrically. So let's say here's my space curve. Actually, sorry, I'm going to erase this, make it, I think, a little easier to do this drawing if I do something like, okay. And let's say the origin is over here. I'm not going to draw the axes to keep this relatively simple. So we'll have, so in the top of this quotient, we have r of t. So let me draw that in. R of t and then r of t plus h is going to be somewhere else on the curve, right? Remember, this function r, this vector function, pops out vectors that are pointing to lines along a space curve. Excuse me, pointing to points along a space curve. So then, between these two, r of t plus h minus r of t is the vector from so I'm not going to write it, it'll be too, it'll get too ugly, but r of t plus h minus r of t is the vector from r of t to r of t plus h. And then we're scaling it by h, or we're dividing by h. But imagine if h is a tiny number, right? As its limit goes to 0, h is getting smaller and smaller. When you divide by something smaller, you make it bigger, right? Divide something by 1/2, you make it twice as big. Divide something by 1/100th, you make it 100 times as big. So this vector, after we divide by h, is going to be some scaled version, right? Same direction, some scaled version of that vector there, okay? And so now we have to imagine, I'll show us an animation in just a moment, but we imagine as h goes to 0, these two red vectors become closer and closer to each other, right? R of t plus h, we're moving backwards along this this curve. So maybe at some time, at a moment when we make h a little bit smaller, that vector will have moved there. And now this green vector, right? The blue vector will have gotten shorter, but so will h, so it'll be scaling it bigger. So it's hard to say if it's going to be bigger or smaller than it was there. That depends on how the limit ends up working out. But there'll be some version of vector, of that vector over here, okay? This vector, this green one, as we take the limit, what it becomes, so maybe I have too many now. In the limit, it becomes a vector that, if this limit exists, it becomes a vector that we will call r prime of t, and we will think of it as the tangent vector to the curve. So dr dt, another name for this, is r prime of t, and r prime of t is the tangent vector tangent let's just leave it at this for a moment, okay? So I've written it as remember from Calc 1, the difference between the derivative as a function and the derivative as a number, right? If you take a function f of x and you take the derivative f prime of x, that's a function that spits out slopes of tangent lines at any point. Well, r prime of t is a function that spits out different vectors depending on where we are along this curve, right? If we evaluate t at any point, we get the tangent vector at that point. So suppose, let's say, r prime of t naught, right, which is going to be equal to x of t naught, y of t naught. Oh, sorry, we haven't gotten that far yet. So r prime of t naught is going to be a tangent vector. I wanted to say, sorry. R prime of t naught is the tangent vector at r of t naught. And let's call point P the point x of t naught, y of t naught, z of t naught. So this just means we evaluate r at some point. We're pointing to a point on the line. We can give that point a name. Okay, so I'm going to erase some of this now. Right, so after we take the limit, we get this tangent vector. All right, so now we're at t naught, r of t naught, and this is our point P. So what we'll do, we're also going to name, we'll say that the tangent line to the curve C is the line through P. Sorry, I'm stumbling with my words today. The tangent line to the curve C at the point P is the line through P parallel to r prime of t naught, right? So if all we're saying here is this tangent vector gives us the direction of the tangent line, right? Just like derivatives in our traditional sense in the real value functions give us the direction of the tangent line, so do these, right? So then there's we can imagine a tangent line to this curve. Pretend I drew it just through that point. It's going to be in the same direction as this tangent vector, right? All right, let's look at oh wait, let's do one more thing before we look at another picture. Actually, no, let's look at the picture first. So let's take a look at maybe a nicer visual here. I'm going to erase some of this stuff. All right, so here we have this gray line is some curve, right? This green one is playing the role of r of t. This blue line is playing the role of r of t plus h. This pink vector is the vector between them, the numerator of our difference quotient, right? R of t plus h minus r of t. And then this red one is the scaled version, r of t plus h minus r of t divided by h. So as I make h smaller and smaller and smaller, right, I'm sliding that blue and green vector closer and closer to each other. Notice the vector between them is getting smaller, but because h is getting so small, it's scaling that red vector much larger, right? And right here, of course, it disappears because now I'm telling the computer to divide by 0. The computer doesn't know how to take limits, but if I just go just before 0, we get a pretty good approximation to what this looks like. There's our tangent vector just coming off the curve there. Right, so we can see this all from another angle, right? We start way out here or wherever, and as we make h smaller and smaller, we get this happening. And we can also see, let's go back to that point where we can see the tangent line, right, is this line that just hits that curve right there, and it's in the same direction as that vector, right? It's kind of being absorbed by that vector. Now let me make it a little bit smaller. Okay, there we go. So there's our tangent line sitting in the same direction as that tangent vector, okay? So we're gonna do very geometrically very similar things, right? We just add these extra dimensions, but we still get these tangent lines and this kind of idea of, well, the idea of still approximating the curve at that point. If I zoom into this tangent point, let's get rid of everything but the tangent line. I guess that's as far as I can zoom in before it stops rendering. So, but we can even see at this level that the curve and the tangent line right there look very, very similar to each other, right? It's kind of laying right on the curve. So it accomplishes a very similar idea. Okay, let's talk about computing these things. Well, it's pretty straightforward to compute them. If you remember from our definition of limits for these vector functions, I can write pretty quickly let's write this, dr dt, which is equal to the limit as h goes to 0 of r of t plus h minus r of t. We're really just going to be able to use all of our limit laws which comes pretty straight from how we define limits for vector functions, r of t. Oh wait, sorry, I skipped a step here. So let me do one piece of algebra, right? If r of t is equal to, so let me mess with this difference quotient for a second. Oops, wrong. All right, if I remember, r of t plus h is going to be x of t plus h, y of t plus h, z of t plus h. R of t, of course, is x of t, y of t, z of t. So when we take the difference, r of t plus h minus r of t, we get x of t plus h minus x of t, y of t plus h minus y of t, and z of t plus h minus z of t. Now, when I divide by h, or I can think of that as multiplying by 1 over h, right? I can just multiply that to each of the components, right? That's our definition of scalar multiplication. So now, this whole thing here is equal to this whole thing here. So this becomes the limit as h goes to 0 of x of t plus h minus x of t over h, y of t plus h minus y of t all over h, and z of t plus h minus z of t all over h. Right? Now I can use the limit laws. We're almost there. The limit as h goes to 0, x of t plus h minus x of t over h. The limit as h goes to 0, y of t plus h minus y of t over t. And finally, the limit as h goes to 0 of z of t plus h minus z of t all over h. Okay, so remember when we define limits for functions, we just said you can take the limit of, sorry, when we define limits for vector functions, we said you can take the limit of each of the component functions. And now look at what we have in each of these components. Those are just regular real valued functions. Okay, and so each one of these individual components should look very, very familiar to us. This is just the definition of the derivative of x as a function of t, y prime of t, z prime of t. And so taking the derivative, right, of course this means as long as all of these limits exist, taking the derivative is as easy as we could imagine. We don't have to learn a whole bunch of new rules. It just means when we take derivatives, we take 3 derivatives, right? That's really all that happens. If you've got a vector function, each component has a function in each component has its own function. When we take the derivative of the vector function, we take the derivative of each vector component function individually. And that will be the vector that spits out our tangent vectors. I want to give one more definition, and then we'll do an example. We also like to define, so remember we've got r prime of t is our tangent vector. Sometimes it's nice, remember how that thing was scaling. It got very large, and at some places it can be very small. We'll find out eventually if we think of these space curves as the path some objects traveling. These things are spitting out velocities, so in some places it's moving faster and some it's moving slower. But we don't always want to capture that information about the size of that vector, the magnitude, which might represent the speed or something else depending on what we're talking about. So we define a new vector. We usually call it t, capital T of t, and it's going to be r prime of t divided by the magnitude of r prime of t, right? And this is going to be, remember what happens when we divide a vector by its own magnitude. We get a parallel vector in this, so a vector in the same direction, but unit size. So this vector here we call the unit tangent vector. Okay, all right, let's do an example. So I'm going to get rid of a bunch of this stuff. We don't need all this. So let's keep this for the moment. All right, so let's take a look at the following function. We've seen this function before. Let's define r of t is equal to t squared, t cubed. Okay. Let's look at r prime of t. Well, we just take, looking at my definitions, I just take the derivative of each of these component functions. The derivative of t is 1. The derivative of t squared is 2t. The derivative of t cubed is 3t squared, right? Just taking each derivative in turn. So this is another function that's spitting out tangent derivatives. Sorry, that was a senseless phrase. This is another function that's spitting out tangent vectors, right? For each value of t, it spits out a vector in the tangent direction. So let's look at, when we evaluate it, r prime of t. This is going to be equal to, so I'm just putting in t equals 2. Sorry, r prime of 2 is what I meant to say. I said t. R prime of 2 is this vector, right? And so what we're saying is at the point when t equals 2, so r of 2 is going to be the point 2, 4, 8. At the point 2, 4, 8, the vector 1, 4, 12 is the tangent vector, right? That's the direction the tangent line should go in. Let's also define, let's look at that unit tangent vector at t equals 2. So we take our, let's take 1 over the magnitude. So we'll have 1 divided by, remember I'm taking the magnitude of r prime. So the magnitude of this is 1 squared plus 4 squared plus 12 squared. And we're multiplying it by this vector, right? So I might write 1 over the square root of 161 times 1, 4, 12, right? So I'm just taking this vector that has magnitude square root of 161 and multiplying it by 1 over square root of 161 and getting a unit tangent vector. Let's do one more thing. Let's write the equation of the tangent line at the point 2, 4, 8, right? So that's the point associated that r of 2 is pointing at. Well, we can write our line equation. I'll write it this way, L of t. I'm just going to put in the point, right? A vector pointing at that point. So let's maybe draw, so maybe there's our curve, there's the point we're at. So I need my, remember what I need for the vector equation of a line. I need a vector pointing at the point, at some point on the line. So my line's gonna look like this. And then I just need a scaled version of a vector in the right direction. Well, the direction is given by the tangent vector, 1, 4, 12. Right? I could also use the unit tangent vector. It's a little bit uglier, so I'm just using the simple, since I don't have any reason right now to use the unit tangent. This gives me the line that touches our curve at the point 2, 4, 8 in this tangent and goes in this tangent direction. Okay, let's take a look at this one with a little bit nicer of a picture. So let me see, which one are we? Yeah, this is the one we want. Let me clear some stuff up. Make a little space over here. Huh, I want this. There we go. Sorry, I was having trouble grabbing it. And let me move most of this out of the way, but I want to save it so we can see what all these pieces look like. All right, so I'll just put this stuff over here. This I don't need. All right, so where are we at? So first, we're looking at a graph of this equation. We've seen it of this vector function. This is the space curve associated to that vector function, t squared, t cubed. Okay, that's what we're looking at here. Let's look at a few things. Let's look at, what do I have? That's not what I want. Ah, there it is. Okay, so first, here's our, let me get rid of this point B. Here's our vector function pointing at points along this line, along this curve, right? So as I scale k, that's the parameter I used, I'm pointing at points on that line, okay? At k equals 2, I need my mouse for this, at k equals 2, right? That's our point right there. Let's look at that red vector, which is too large to see, but it's pointing in this direction. That's our tangent vector. That's the vector we came up with, 1, 4, 12 at that point. Here's the unit tangent. Oops, sorry. Here is the unit tangent. Right, so it's much smaller. If I rotate around, we kind of see it sitting on top of it. It's just, all they're really showing is the top of the arrow there because it's so small. And then if I draw the tangent line, it looks like that dotted line. Let's get rid of the axes, right? So if I zoom in a little bit, there we go, this is better. All right, so, it's hard to manipulate this thing the way I want. But in any event, that red vector is, so there's the origin at the letter A there. The black vector is pointing at our function, this curve, and the red vector is the tangent vector, and that dotted line is the tangent line. And I set this up so we can see that at each point, right, we're getting different. This is thinking of the vector derivative as a function. It's spitting out the tangent vector at each of those points and then constructing the line based on that tangent vector, right? So we see this nice, we get tangent lines everywhere for our function. It does something interesting in here. Let's look at it from this direction. Now I'm kind of looking down the z-axis, right? In this direction, we actually see something sort of familiar. There's a looks like a parabola from this direction. If we forget that we're in 3 dimensions, this is just spitting out tangent lines to that parabola, right? It's kind of easy to see in this direction. Okay, let's stop this one there. We'll do some more examples of derivatives. We'll do some integrals in some later videos and see that it works out just as well. Though we'll have to, the meaning is going to be a bit different. But in terms of computing them, there's no big, no new things we have to do. Okay, thanks everybody. I will see you next time.